Hi everybody, this is Dr. Nigro with a Physics Fundamentals screencast. The screencast is going to look at electrical power and electrical energy. All right, so we're going to start with the definition of electrical power. We've talked about power before. We were talking about mechanical power, but it's the same general idea. All right, it measures the rate of energy usage. All right, when we were talking about mechanical power, it was the rate at which work was done. When we talk about electrical power, it's the rate at which the electrons do work as they move around the circuit. All right, so our formula, generally speaking, can just be energy divided by time. That's our rate. All right, and just like we saw before, the unit is going to be the watt again. And remember, a watt is actually a joule per second in terms of compound units. All right, now, because we're not dealing with work this time, we actually are going to calculate power slightly differently. We know that power is equal to joules times seconds, so that means we can multiply voltage times current and we can get back to that unit, because if you think about it, a volt is just a joule per coulomb, and a current, an amp, is just a coulomb per second. So if we multiply those two together, we end up with this joule per second, or the watt. All right, now, what if we don't know voltage and or current? All right, there are other options. We can use Ohm's law for substitutions. All right, so remember, the voltage is equal to the current times the resistance. And with that in mind, if we don't know the voltage or the current, but we do know the resistance, then we can start to use that and make some substitutions. So the question then becomes, well, when do we use them? All right, so when the voltage is constant, all right, this happens in parallel circuits. Sorry, I was about to write series. Circuits. This also is the case when you're talking about appliances or different electrical devices in your home that are plugged into a wall outlet. In those cases, the voltage is constant because the outlet only comes in at one voltage. There's no knob on the side of the outlet that lets you dial up or down the voltage like we see on our power supplies in the classroom. So that case, we're going to have a constant voltage. And in that case, we're going to use power is equal to voltage squared divided by the resistance. Now, you might ask, well, how did I come up with that? Well, remember, all right, we've removed current from this. And so we know based on Ohm's law that current equals voltage divided by resistance. So if I plug that in for the current, then I'm going to end up with V squared over R. All right, so you can see that the relationship between power and resistance here is an inverse relationship. As the power goes up, the resistance goes down, and vice versa. All right. Whereas the relationship between the voltage and the power is still a direct one, just like we saw before. All right. When current is constant, all right, this happens in series setups. All right, now we don't have many of these outside of the lab and Christmas lights. All right, but it can happen. And when that happens, we need to remove voltage from our equation. So we use Ohm's law again, and we solve it for voltage, which we know is I times R. We plug that in for voltage in our power formula, and we end up with current squared times the resistance. All right, now, in this case, you can see that power and resistance are directly related. So the relationship between those two variables is going to change depending on what is being held constant, the voltage or the current. And that's really important to keep in mind when you're answering questions about power versus resistance. So make sure you pay attention to the problem and that you are clear on what is staying constant, and then use the appropriate formula and that appropriate relationship. All right, now, what if we want to measure the energy that's being dissipated? All right, and that means the energy that's being converted from one form into another. And that conversion tends to be potential energy, the voltage, to some sort of energy such as heat. We could get light. You could get mechanical. All right, there are a lot of different choices for how that energy can be transformed into something else. And we know it has to be transformed because if it weren't, we'd be destroying it, and that is not allowed per the law of conservation of energy. So to measure that amount, we're going to take our power formula over here and we're just going to rearrange it and solve it for energy. So energy will be equal to power times time. All right. Now, if we want to use this formula, we can keep it in watts times whatever time unit we have. But a lot of the times you're going to see this unit, kilowatts times hour. So this is a kilowatt hour. Sorry, that didn't look quite right. All right. And what that means is the power needs to be in units of kilowatts and your time needs to be in units of hours. This is actually what the power company and the electric companies use when they're calculating your rate that you need to pay. They determine the amount of energy that you have used over a particular amount of hours, usually the hours within a month. All right. And then from there, they set a rate. And let's say, I don't know, 15 cents per kilowatt hour. And then they multiply the amount of energy used by that rate, and then they can figure out the cost. Okay. So if you need to calculate the energy, you're going to want to go back to that power formula, power times time. And if you don't know the power, if you instead have velocity, voltage, and current, then you're going to need to solve for power and then find that energy that's been dissipated. Okay, so let's try a couple practice problems. These are pretty straightforward, but just in case. All right, so this first one says, how much power is used by a contact lens heating unit that draws 0.07 amps of current from a 120 volt line? All right, so I always like to list out what I have been given. All right, so I have a current value of 0.07. I have a voltage of 120 volts. And I'm looking for not resistance. I'm stuck on my Ohm's law. I'm looking for power. All right. So I look at those variables and I think about my formulas and I know that power is equal to current times the voltage. So I have both those values. So I just set them in there, 0.07 amps times 120 volts. And we're going to get a power value of 8.4, and that's going to be in watts. Okay. So that one's pretty straightforward. Let's try another one. Find the resistance of a 1400 watt microwave oven designed to run on 120 volts. All right, so I have a voltage of 120. I have a power value of 1400 watts, and we're asked for the resistance. All right, so we don't have a formula per se that relates these three variables, so I'm going to need to use my power formula, P equals V times I, but I'm going to need to substitute. And I'm going to do that substitution per Ohm's law. All right, so what does that look like for this particular problem? I'll put it up here. We know that voltage is current times resistance, which means current is equal to voltage divided by resistance. So I'm going to plug that in, and I end up with power is equal to voltage squared divided by my resistance value. All right, so I plug in what I've got. 1400 watts is going to be equal to 120 volts squared divided by my resistance. I rearrange and solve, and I find that this particular microwave has a resistance of 0.3 ohms. All right, so again, not difficult, but you need to make sure that you're utilizing the substituted formula. Okay? I guess another option, if you wanted to, you could go into Ohm's law. No, you can't do that either because you don't know the current. So this is going to be your best bet, to use Ohm's law, substitute the variables in, and then solve. All right, so now we have an electric motor with a resistance of 0.25 ohms that produces 100 watts of power. How much current does it draw? All right, so we have a resistance of 0.25 ohms. We have a power of 100 watts, and we're asked to find the current. All right, so again, my power formula relates voltage and current, but does not include resistance. All right, and I don't have the voltage here. So again, I'm going to use voltage is current times resistance, but I'm going to solve this time for voltage. Oh, well, I've already solved for it. So I'm just going to plug in current times resistance into my power formula. So power is going to be equal to current squared times the resistance. All right, so in this case, we have 100 watts. It's going to be equal to I squared times that resistance of 0.25 ohms. I'm going to rearrange, and I'm going to get I squared equals 400. And then when I take the square root of both sides, the current here is going to be equal to 20 amps. All right. Jane uses a 1200 watt hairdryer for 12 minutes before school. How much electrical energy does she use in kilowatt hours? So we're looking for an energy value here, and we have a particular unit. All right, so what do we have? We have power, 1200 watts. We have time, 12 minutes, and we're asked to find the energy. All right, so we need the watts in kilowatts. All right, so to go from watts to kilowatts, I need to divide by 1,000. So this is 1.2 kilowatts. And we need that time in hours. So I need to divide my minutes by 60 to get to hours. So that's going to be 0.2 hours. So that gets the units in the right spot. Now remember, power is equal to energy divided by time, which means that energy must be equal to power times time. So I plug in my kilowatts, 1.2 kilowatts, and my time as hours, 0.2 hours, which means the energy is 0.24 kilowatt hours. All right, that's the amount of energy that she's using with that particular hairdryer when she runs it for 12 minutes before school. All right, if the electric company charges 0.15, so 15 cents per kilowatt hour, how much would it cost Jane to use her hairdryer for 12 minutes daily for 30 days? All right, so I know the power. It's going to be 1.2 kilowatts. All right, but my time's going to be a little different. It's not just 12 minutes. It's 12 minutes each day for 30 days. So my time is going to be 12 minutes times 30 days. All right, so when I multiply those two together and then convert to hours, I find that this equals 6 hours. All right, so I need to figure out what the energy is first. So that's going to be power times time. So 1.2 kilowatts times 6 hours. Oops, sorry, that's terrible. 6 hours is going to be 7.2 kilowatt hours. All right, so that's the amount of energy she's used over this month using her hairdryer every day for 12 minutes. All right, so the question now is, well, then what does it cost? All right, so we have 7.2 kilowatt hours, and the electric company tells us that they're going to charge us 15 cents for every 1 kilowatt hour. All right, so these units are going to cancel. If we multiply 7.2 times 15 cents, we find it's going to cost $1.08. All right, which doesn't seem like that much, but that's not the only thing that's running in your house, so it all adds up. I tell you that. All right, one more problem. All right, a heater has a resistance of 25 ohms and operates on 120 volts. How much current is supplied to the resistance of the toaster? All right, so let's start with what we know. We have a resistance value of 25 ohms, right? And we have a voltage of 120 volts, and we're asked to find the current. All right, so the current is going to be equal to the voltage divided by the resistance. So in this case, 120 volts divided by our 25 ohms. All right, plug that into our calculator, and we find we have a current of 4.8 amps moving through the resistance within the toaster. All right. Now it says how many joules of energy are provided by the heater in 5 minutes. All right, so let's list what we have again. So we have a voltage of 120 volts. We have a resistance of 25 ohms. We know we have a current of 4.8 amps, and now we have a time of 5 minutes, which I'm going to go ahead and convert into seconds. So multiply it by 60, 300 seconds. And we're asked to find the energy. All right, now I don't have a formula that's going to get me straight there. All right, I could find potential energy, but that's a little tricky because I don't know what the charge is. There are multiple ways to work your way through, but I do know that energy is equal to power times time, and I have time. So the question is, can I calculate the power with what I've got? And the answer there is yes, because power is equal to voltage times the current. All right, so in this case, 120 volts times our 4.8 amps is going to give me a power of 576 watts. All right, and with that in mind, I can go back to my energy formula. So energy is going to be equal to 576 watts times that 300-second time frame. And if I multiply that out, 72,800 joules of energy are being provided to the heater during this 5 minutes. Okay? All right, so those are just some different examples of power and the power formula and then energy. All right, again, it's really important that we remember this relationship. All right, now obviously power equals voltage times current is important. But a lot of the times the questions come back to, well, what's the energy? So you need to be able to go from our voltage, current, resistance values to energy. And the way to do that is through that formula that the power that is being supplied is equal to the energy being used divided by time, the rate at which that energy is being used. Okay?